नमस्कार दोस्तों, स्वागत है आपका भारद्वाज गुरुकुल में, जहां सीखना होता है आसान और मजेदार। आज हम क्लास 10 आईसीएसई फिजिक्स के एक बेहद जरूरी चैप्टर को आसान भाषा में समझेंगे, वर्क, पावर एंड एनर्जी। तो चलिए शुरू करते हैं वो सफर। आज हम सीखेंगे वर्क, पावर एंड एनर्जी इन द मोस्ट सिंपल, विजुअल एंड एग्जाम ready way. In this video, we will learn what is work, factors affecting work, power, energy and its types, potential energy and kinetic energy, linear momentum, law of conservation of energy, and numericals and the related concepts. Why a coolie does no work while carrying some load on his head? Or how does a washing machine actually work? Or why does energy always remain constant? These everyday experiences are beautifully explained by the concept of energy, which we will explore today in depth. So let's begin.
Chapter Work, Energy and Power. Work. When a force applied on a body makes the body move, the work is said to be done on the body. That is, whenever force is applied, then the body moves, then work is said to be done on any body. SI unit of work, Joule or Newton per meter. Relation between SI and CGS unit of work. Work is equals to Fs. 1 joule is equals to 1 Newton into 1 meter. So 1 joule is equals to 10 the power 5 Dian, because 1 Newton is equal to 10 the power 5 Dian, and 1 meter is equal to 10 the power 2 centimeter. So 1 joule is equals to 10 the power 7 Dian centimeter, or 10 the power 7 ergs. Factors affecting work done. Magnitude of force, that is F, displacement S, and the angle between F and S, that is theta. Special cases. Case 1. If displacement is along the direction of force, that is when the theta is equals to 0, then work is equals to Fs cos theta and the work done will be maximum. Example, a force applied on a book displaces it horizontally. Case 2. If displacement is opposite to the direction of force, that is when theta is equals to 180 degree, so work done will be in minus, so work done will be minimum. Example, friction. It always acts opposite to the displacement. A body thrown vertically upwards has its weight acting downwards. In a single fixed pulley, force is applied in the downward direction, but displacement is in the upward direction. A bucket is pulled from a well. So these were the examples when the angle between the two is 180 degree. Case 3. If force and displacement are perpendicular to each other, that is when theta is equals to 90 degrees, so work done will be 0. Example, a coolie carrying a luggage on his head does no work. Now let's move to the second topic, power. The rate of doing work is called power, or work done per unit time is known as power. So power is equals to work done upon time. SI unit of power, watt or joule per second. Note point, in physics, power is estimated by the rate of doing work, that is faster or slower, and it does not mean to have any relation with the strength. Means if a body is having more power than the other, that means the body is able to do the work faster than the other body. Question, power can be expressed as a product of force and velocity. Explain. So as we know, power is equals to work done upon time, and work done is equals to force into displacement. So displacement upon time is velocity, so power can be expressed as the product of force and velocity. Third topic, energy. The capacity to do work is called energy. Types of energy. Kinetic energy. The energy possessed by a body by virtue of its motion is known as kinetic energy. The formula is K is equals to 1 by 2 mv square, where K is the kinetic energy, m is the mass, and v is the velocity. Potential energy, gravitational potential energy. The energy possessed by a body by virtue of its position or height is known as gravitational potential energy. Its formula is U is equals to mgh. Elastic potential energy. When a string is compressed or expanded, then a restoring force acts on the spring and some work is done. This work is stored in the form of elastic potential energy in the string. You can see when force is applied, the distance x elongates. So the restoring force F is equals to minus kx, where k is the spring constant and u is the elastic potential energy. Other forms of energy: chemical energy, heat energy, sound energy, light energy, electrical energy, and many more. Work energy theorem. According to this, work done on a body is used to change its kinetic energy. So the formula for work energy theorem is W is equals to delta K. Proof: W is equals to Fs, W is equals to Ma into V square minus U square upon 2A. W is equals to 1 by 2 M V square minus U square. So W is equals to 1 by 2 Mu square minus 1 by 2 Mv square. So W is equals to kinetic energy final minus initial kinetic energy. So work done is equals to delta K. Linear momentum. It is defined as the product of mass and velocity of the body, or the motion contained in a body is known as linear momentum. Formula is P is equals to mv, SI unit is kg meter per second. Relation between kinetic energy and momentum. P is equals to mv, K is equals to 1 by 2 mv square, multiplying and dividing by m, K is equals to 1 by 2 m square v square upon m. K is equals to mv whole square upon 2m. K is equals to p square upon 2m. P square is equals to 2mk. Law of conservation of energy. Energy can neither be created nor be destroyed. Only it can be transformed from one body to another. When a body is thrown vertically upwards, its kinetic energy changes to potential energy, and when a body is dropped from a certain height, its potential energy changes to kinetic energy. So kinetic energy at bottom is equals to potential energy at top. So V square is equals to 2gh, so V is equals to under root 2gh. Now question: state the energy conversion taking place in the following cases. Washing machine, electrical to mechanical energy. Steam engine, heat to mechanical energy. Microphone, sound to electrical energy. Loudspeakers, electrical to sound energy. Electric bulb, electrical to heat and light energy. Photosynthesis, light to chemical energy. Electrolysis, electrical to chemical energy. Rubbing of palms, mechanical to heat energy. So now let's show that during any vertical height, the total mechanical energy remains constant whenever anything falls down or goes up. At topmost point C, over here, PE is equals to mgh, kinetic energy 0. So total energy mgh plus 0 is equals to mgh. At midway point, potential energy is equals to mgh minus x. Kinetic energy 1 by 2 mv square. V1 square is equals to 2gx according to the motion equations. Kinetic energy is equals to 1 by 2m plus 2gx. Kinetic energy is equals to mgx. So total energy is equals to mgh minus x plus mgx. So total energy again is mgh. At bottommost point, potential energy is equals to 0. Kinetic energy is equals to 1 by 2 mv square. V square is equals to 2gh. Putting values, kinetic energy 1 by 2 m into 2gh. So kinetic energy is equals to mgh. Total energy is equals to 0 plus mgh. So total energy in the third part is mgh. So from equation 1, 2 and 3, we conclude that the total mechanical energy remains conserved. Energy conservation in a simple pendulum. At extreme position, the bob of simple pendulum has potential energy only. At mean position, it has kinetic energy only. According to the law of conservation of energy, kinetic energy of mean position is equals to potential energy of extreme position. V is equals to under root 2gh. Now let's move to numericals. First, a force of 15 Newton is required to pull up a body of mass 2 kg through a distance 5 meter along an inclined plane, making an angle 30 degree with the horizontal. Calculate work done by the force in pulling the body. force due to gravity, work done against the force of gravity. Account for the difference in answers of part first and third. So first part, W is equals to Fs cos theta, putting the values. Work done is equals to 15 into 5 into cos 0 degree, that is 1. So work done will be 75 joule. Second part, force is equals to mg, so force is equals to 2 into 10, that is 20 newton. Third part, work done is equals to mgh, so work done is equals to 20 into 2.5 is equals to 50 joule. Fourth part, difference 75 minus 50 joule, that will be 25 joule. 25 joule energy is lost in the form of heat to overcome friction. Second, a boy of mass 40 kg climbs up a flight of 30 steps, each 20 cm high in 2 minutes, and a girl of mass 30 kg does the same in 1.5 minutes. Compare the work done and the power developed by them. Boy m1 is equals to 40 kg, height is equals to 6 meter, and the time taken is 2 minutes. Mass m2 of the girl 30 kg, height is same 6 meter, and time taken is equals to 1.5 minute. We have to calculate the ratio, so work done m1gh upon m2gh. We'll do the calculation, it will come 4:3. On comparing the powers, work done upon work done into time taken by the boy upon time taken by the girl, so it will come to be as 1/1, that is they generate the same power. Question 3. A pump is used to lift 500 kg of water from a depth of 80 meter in 10 seconds. Calculate the work done by the pump, power at which the pump works, power rating of the pump if its efficiency is 40%. First part, mass is equals to 500 kg, time is equals to 10 seconds, height 80 meter. So work done is equals to mgh, work done is equals to 500 into 10 into 80, 4 into 10 the power 5 joule. Second part, power output is equals to work output upon time, 4 into 10 the power 5 upon 10, so the power output will be 4 into 10 the power 4 watt or 40 kilowatt. Third part, efficiency, power output upon power input, so 1 by 100 is equals to power input, so power input will come as 100 kilowatt. A water pump raises 50 liter of water through a height of 25 meter in 5 seconds. Calculate the power of the pump. So V is equals to 50 liter, 50 into 10 the power minus 3, we will convert it into meter cube. Then L is equals to 10 the power 3 kg per meter cube, M is equals to V rho, putting values 50 into 10 the power 3 into 10 the power 3, so mass will come as 50 kg. Power is equals to work done upon time is equals to mgh upon time, 50 into 10 into 25 upon 5, so power is equals to 2500 watt, that is 2.5 kilowatt. In a dam, water falls at the rate of 1000 kg per second from a height of 100 meter. Calculate the initial potential energy of the water. Second part, assuming that 60% of the energy of the falling water is converted to electrical energy, calculate the power generated. First part, potential energy is equals to mgh, so potential energy is equals to 1000 into 10 into 100, you will solve it the answer. Second question, electrical energy is equals to 60 upon 100 into potential energy, 60 upon 100 into 10 the power 6, so 6 is equals to 10 the power 6 into 10 the power 6 joule. So putting the value of potential energy, power is equals to potential energy upon time, so 6 into 10 the power 3 upon 1, so 600 kilowatt. Calculate the kinetic energy of a body of mass 0.1 kg and momentum 20 kg meter per second square. Mass is equals to 0.2 kg, momentum 20 kg meter per second square. Kinetic energy is equals to p square upon 2m, putting values 20 whole square 2 into 0.1 is equals to 400 upon 0.2, so kinetic energy will be 2000 joule. How is the kinetic energy of a body affected if its mass is doubled, its velocity is reduced to 1/3 of the initial velocity? Kinetic energy is equals to 1 by 2 mv square. M1 is equals to 2m. K1 is equals to 1 by 2 m1 v square. K1 is equals to 1 by 2 2m v square. So K1 is equals to 2k. Second part, V1 is equals to V by 3. K1 is equals to 1 by 2 mv square. K is equals to 1 by 2 m v upon 3 whole square. K1 is equals to 1 by 9 into 1 by 2 mv square. So K1 is equals to k upon 9. For the same kinetic energy of a body, what should be the change in its velocity if its mass is increased 4 times? K1 is equals to 1 by 2 m1 v1 square. K is equals to 1 by 2 m2 v2 square. K1 is equals to k2, which is given. 1 by 2 m1 v1 square is equals to 1 by 2 m2 v2 square. 1 by 2 gets cancelled. m1 v1 square is equals to m2 v2 square. m2 is equals to 4 m1, which is given. m1 v1 square is equals to 4 m1 v2 square. v2 square is equals to v1 upon 4, so v2 is equals to v1 by 2. A ball of 10 gram falls from a height of 5 meter. It rebounds from the ground to a height of 4 meter. Find initial potential energy of the ball, kinetic energy of the ball just before striking the ground, kinetic energy of the ball after striking the ground, the loss in kinetic energy on striking the ground. So first part, mass is given as 10 gram, which is equal to 1 by 100 kg. Height 1 is 5 meter and height 2 is 4 meter. We have to calculate potential energy, which is mgh1, 1 upon 100 into 10 into 5, so 0.5 joule. Second part, kinetic energy before striking is equals to potential energy at A, kinetic energy before, so this will also be 0.5 joule. Third part, kinetic energy after striking, potential energy at C, kinetic energy after mgh2, so 1 upon 100 into 10 into 4, 0.4 joule. Fourth part, kinetic energy is equals to kinetic energy before minus kinetic energy after. So delta kinetic energy 0.5 minus 0.4 is equals to 0.1 joule. Kinetic energy is lost in the form of heat and sound energy.
Quick tips for success. The concepts of work and energy are not just theory, they describe our world. Mastering them makes you understand how everything works. So keep practicing those formulas and solving questions. उम्मीद है आपको ये वीडियो पसंद आया होगा और वर्क पावर एंड एनर्जी अब पहले से काफी आसान लग रहा होगा। अगर हाँ, तो वीडियो को लाइक और शेयर जरूर करें और भारद्वाज गुरुकुल को सब्सक्राइब करना ना भूलें ताकि आप कोई भी जरूरी चैप्टर मिस ना करें। नीचे कमेंट में बताइए कौन सा चैप्टर आपको अगला चाहिए। मिलते हैं अगले वीडियो में, तब तक के लिए पढ़ते रहिए और आगे बढ़ते रहिए।